Alright, so we're going to look at an example problem where a parallel plate capacitor has a charge of 0.5 nanocoulombs and the distance between the plates is 5 millimeters and the area of the plate is 7 centimeters squared. First, we want to know what the capacitance of the capacitor is. So since we know this is a parallel plate capacitor and we have the dimensions of it, we can use the idea that capacitance equals the electric constant times area of one of the plates divided by the distance between the plates. So I can plug in my electric constant. And nicely, now that we're in capacitance, the units for the electric constant can also be farads per meter, which is much nicer than remembering a newton meter squared per coulomb squared. Then we're going to multiply by the area. So be careful when you convert the area, you have to convert both centimeters to meters. So it becomes 7 times 10 to the minus 4 meters squared rather than 7 times 10 to the minus 2 meters squared. And then we have to divide by the 5 times 10 to the 3, which is the meters, which is the distance between the plates. And this is going to equal 1.24 picofarads, or 1.24 times 10 to the minus 12 farads. We then want to know what the potential between the plates is. And since we know the charge on one of the plates, we can use the fact that we also now know the capacitance to find the potential between the plates. So we're going to plug in our 1.24 times 10 to the minus 12, which is going to equal 0.5 times 10 to the minus 2 coulombs, divided by the potential, and the potential turns out to be 403 volts. And now we want to know what the electric field between the plates is. Now, because this is a parallel plate capacitor, and the electric field does not have a dependence upon the distance between the plates, we can simply write the potential between the plates is equal to the electric field times the distance between them. So we can plug our 403 volts equals the electric field times the distance between the plates, so 5 times 10 to the minus 3 meters. And that's going to give us an electric field strength of 8.06 times 10 to the 4 newtons per coulomb. And I want to emphasize once again that the relationships that we're using, so our capacitance equation for part A and our potential equation we used in part C, are specific to a parallel plate capacitor. So if you started with a cylindrical or a spherical capacitor, you would have had to use different relationships to answer A and C.